Hello and welcome to part 3 of the creating a two-wheeled robot demo. Here we're going to try and start to add some sensors. So there's two sides to adding a sensor. We're going to add the embedded code and then we're going to add the code to drive the simulation. To do this we're going to create two separate macros. So I'll start with the embedded side code. For the embedded side code we're going to need something along the lines of an analog input. So I'm going to use a potentiometer component, and I can set the pin connection here. So I'm going to set it to pin RA2 or analog input 2. I'm also going to use an output. So I'm going to create an extra property. So I'm going to add new. I'm going to call this the infrared enable pin. I'm going to change the property type to a single digital pin. The property variable is IR enable. I'm going to connect that to pin A3. I'm then going to create a new macro, and I'm going to call this read IR sensor. Reads the IR proximity sensor. Returns the range 0 to 255 representing max proximity. I'm going to set a return variable to a byte, so I'll give it 0 to 255. And then inside the macro, I'm going to create a variable which is our IR reading 1, IR reading 2. I'm going to sample the analog inputs, so I'm going to read the potentiometer, get bytes, and I'm going to store that into our local variable IR reading 1. I'm then going to switch on the infrared output, and I do that by using a calculation icon to refer to the property that we made, so IR enable. I'm going to assign that the value of 1, so it's going to light the infrared LED. And I'm going to use a very small delay, so maybe 10 microseconds, to allow the infrared sensor to react. And then I'm going to read the potentiometer again, so get byte, and this time I'm going to store it into IR reading 2. Once I've done that, I'm going to switch the infrared LED back off to save battery power. And I'm then going to add a final calculation to say the return value is equal to IR reading 2 minus IR reading 1. What this does is it takes a reading when the infrared switched off, and then it switches the infrared on and takes another reading. This second reading, we subtract the first reading from this, and that gives us the infrared light level regardless of what the ambient light level is currently reading. So that's the code to drive the embedded side functionality. To do the simulation side things, what I'm going to do is I'm going to create a second macro. So I'm going to right click this macro and duplicate. I'm going to call this one read IR sensor underscore sim. This is going to do exactly the same thing, but it's going to do the simulation code to actually detect other objects on the panel. To get this simulation override to work, so when we call this function, this one will be compiled and downloaded to the chip, and this one will be executed when we simulate. To do that I go to the interface manager, and I click on the read IR sensor macro, and I set that to be downloadable. And then you see I get a simulation macro currently it's set to be itself, and so I'm just going to add the underscore sim, and then that allows this macro to be ran whenever we're doing simulation and this macro to be downloaded. While I'm in here, I'll set all the other functional macros to be downloadable as well. Set PWM as a private macro, so we don't need to expose that one. Okay. Save the project. So now, let's create the simulation side of things. To do this, I'm going to start with an object. So here I've got another cube, and in the position properties, I'm going to shrink this down a bit. So instead of 32 by 32, let's try 1 by 1 by 1. It's maybe a bit small. Let's try 5 by 5. That's a bit better. And let's change the colour just to make it a bit more obvious which is the sensor. Make it yellow. Oops. Let's set it in the right place. There we go. Now the cube for the body is currently located at 0016. So let's set the position of our sensor cube to be let's try 10, 0, 10, 32. Let's see how that looks. That's pretty good. So what we're going to do is we're going to use this to beam forward a line. In fact, let's take it forward a bit further. 10. Let's make it 16. That's a bit better. And that's going to be the front of our robot. Is it hovering a bit? Yes, it is. Let's just bring it down a little bit further. 30. That's better. Okay. So I'm going to right click, I'm going to click the object, and then here I'm going to give it a name that we can refer to. So I'm going to call this IR sensor. So let's go into our read IR sensor sim component macro. Let's delete the code that's in there, and let's create some new variables. We don't need the IR reading 1 and 2 anymore, so let's get rid of those. What we do need is we need a position handle object. And we need a byte to determine when we've touched something. So we'll call this touch. So we're going to start by assigning our position handle. We're not going to use a calculation icon for that. We're going to use instead a simulation API macro. So under functions, and it's panel position get. The handle of the object that we want to get is our IR sensor, and we're returning the value into our local position handle variable. So that just takes the position of this cube and assigns it into this object variable. The next thing we're going to do is under functions, we're going to use panel position move along. The handle is our local position handle. The axis is this. So whenever this refers to our component space, so whenever the component is dragged onto a user's panel, it will always be the direction that that's facing. And then we probably want to move by Y. What we're trying to do is get the cube, the position from the cube that we've taken, and we want to move it so it's not touching the robot anymore, just so we don't get a false collision when we're doing eye detection. So I'm going to try and move this by 20 in the y-axis. The y-axis is here in green, so red's x, y's green, blue is z. I'm just going to have a look to see how this is running. So I'm going to set a breakpoint here. In my main, I'm going to call the read IR sensor sim macro, and in view I'm going to look at the component debugger window. Just going to clear the text. In here are some options to help debug components, and you can do things like show position objects. So I'm just going to tick that, and that allows me to see certain positions. You can see that there's some positions already going on the panel. So if I run this now, you can see it's taken the position of our cube, and we've hit our breakpoint. So if I step, you can see that the cube has moved outside of the robot. That's probably a bit far, so let's stop the simulation and just edit this again. Let's set it to 10 instead of 20. So the position object starts on the cube, and you step, and it moves outside of the robot. Okay, so that's perfect. Let's get rid of those. Okay. So now we want to create a loop, and we've got a return variable. We're going to assign our return, so dot return equals 255. So we're going to initialize it to be the closest proximity it can. 255 is max proximity. And in our loop, we're going to say while dot return is greater than 0. Inside our loop, we need to decrement the return. Return equals return minus 1. So this will loop around from 255 times until return 0, and then it'll drop outside the loop and return. Also inside the loop, we want to move along the center again. So position handle is our handle. Again, the axis is this. The y this time, let's say we want to move it by 2. So now if I add a breakpoint here and run this, oops, switch on our position objects again. Now I can press play, and every time the sensor will move out by the resolution that we've set. Okay, so that seems to be working fine. The next thing we want to do is detect to see if there's been a collision made. So again, we're going to use the API functions. This time it's panel collision get multi-axis. The position is our local position handle variable. The X, Y, and Z, these are, if there's a, we can assign variables to these, and if there is a collision, these will populate with the values needed to move out of the collision situation. We're not going to use those, so we're just going to assign a float value 0.0. The target space is also 0. This means that it will scan everything on the user's panel once we've exported it to component. And our return value, which we use our local touch variable. Then we just need a quick decision. If .touch is greater than 0, so 0 is nothing's been hit. Greater than 0, something's been hit. And what we do is we create a go-to point and a reference to that to jump outside the loop. So if we hit something, then the return should be greater than 0, otherwise we stay in the loop until the return value is 0 and then we exit on our own. So I'm going to save this and I'm going to export the component. I'm just going to fill in some details about what the component's going to be called. So I'm going to call it two-wheeler. The author's Ireland. Under advanced, we can set the GUID. Just make sure that this is unique. If there's a name here, then you can click edit and new, and that assigns it to a new component ID. We want to show the component in the let's put it under mechatronics. Description: simple two-wheeled robot. Let's just check our interface. So here you can see all the macros that have been exposed. So we can go forwards, backwards, spin left, spin right, stop, and read the IR sensor. More importantly, this one has a simulation override to call this function instead when we simulate it. Resources, we don't have any resources. If we're using mesh files, then we could put our mesh files in here, and then when we export the component, our mesh will be included. I'm just using primitives, so it doesn't matter, I don't need those. So, save changes, and then it asks me to export my component file. I'm going to pop it on my desktop. In View Global Options, under Locations, you can actually assign folders to look in for components. So you don't have to rely on the lockdown program files folder. So now if I go File New, now I'm going to create a new project. I'm going to select the target device. That would only matter once you've actually picked a chip to run your robot on. From mechatronics, I'm going to drag on the two-wheeler. So here's our robot component. See, there's our sensor on the front. And then let's look about creating a simple program. So I'm going to initialize the robot. And I'm going to create a loop. And inside the loop, I'm going to read the infrared sensor. And store that value into a byte variable, call it IR. I'm going to say if IR is greater than 200, then we're going to spin, speed 100. If the IR is not greater than 200, then we're going to drag forwards at speed 100. And then I'm just going to add a bit of a delay, so let's have 10 millisecond delay. And then let's create some walls to go around the robot. So I'm just dragging on the primitive again, and then under position, let's make the width 200. Let's try 2000. Better. Make this bit bigger. So copy paste that, and copy paste again. This time I'll rotate it around the Z axis, so 90 degrees. Let's see, this is minus 1000. Oops, let's put this at plus 1000. Just zoom out a bit. There we go. perspective, makes it look a bit better. Maybe 1,000 is too much. Let's set them again to say 1,000 and then 500 minus 500, 1,000. This one, width is 1,000. 0, 500. Copy paste. This one should be minus 500, 0. Let's get the Z's all the same, so 16 already, and 16. So hopefully we've got a bit of an inside wall now that we can see if our collision detection is going to work. So it's a bit bigger. Save this, give it a name, test, and click play. You can see that with one sensor, the robot's still having problems maintaining its distance from the wall. So with a robot like this, you'd normally have one at the front, and maybe one at each side, and maybe another one at each corner, and then you can tell as you're turning how far away from the wall you are at all points. Many thanks for watching. I hope you've enjoyed my series on how to create a two-wheel robot.